yeah, thanks for letting me talk. You may have heard that yesterday there was a announcement, Nobel Prize in Physics in quantum information, which is very exciting. So they were awarded to first doing the so-called like Bell test, which really established that nature is based on quantum mechanics. And these days, there's not just academic interest, but also industrial interest in leveraging this quantum information to do something useful. I think in that endeavor, quantum error correction is, I think, crucial. And I'm going to give you sort of a review slash like sort of my research talk today, so that you're set up to listen to other talks in the future for the external speakers. So let's begin. I did some work in the industry before I came to UC Davis, and it's been interesting to see the so-called quantum computing industry grow like pretty rapidly. So this is a slide that I stole from a conference called like Q2B. It's an acronym for Quantum to Business. And what you can see is that this plot is a bit outdated, but you can see that from 2017 to 2020, this was right before the pandemic, and the number of participants have been growing fairly rapidly. And this is also accompanied with the fact that there's a lot of not just like non-quantum computing companies that are interested in quantum computer, but also the fact that there are actual quantum computing companies which are trying to build the hardware, and also software. So here I just listed the hardware companies because the software companies, there are too many of them. I simply won't be able to like list them all. So this is a growing field. And so the natural question, if you're new to this field, is like, why do people care about quantum computing in the first place? The short answer is that it's because there are some compelling applications. So to be clear, the quantum computers that we have these days are not powerful enough to do something useful right now, but we have good reasons to believe that we can make them at a larger scale. And moreover, we have good reasons to believe that once we make them, we can do something useful with it. So perhaps the most famous application of all is maybe not the most societally beneficial one. It's breaking public key crypto system by Peter Shor, first discovered in 1994. But it was really a compelling evidence that quantum computer can do something that the classical computers cannot. So to be clear, it's not like we don't know that we can't break the existing crypto systems using classical computers, but people have tried for many decades. So at this point, given that many smart people have worked on it and have failed to crack it, probably the classical computers are unable to break the crypto systems that we use. But Peter Shor showed that if you can build this thing called quantum computer at a large scale, you can solve this problem efficiently with this hypothetical device. And perhaps this is like less impressive, but in fact, people found out quickly after Shor's discovery that if you have a quantum computer, you can get a generic like quadratic speedup. So this is very different from what you have for Shor's factoring algorithm, which provides an exponential speedup over all possible all known classical algorithms. But it does show that quantum computers are in some sense like more powerful than classical computers in general. But for right now, I think what is believed to be the most compelling application of quantum computer in the near future is likely to be simulation of quantum systems. So the physical systems that actually appear in nature. And this idea was first proposed by like Richard Feynman, famously back in 1980s. But since then, people have revisited this idea. And there's currently a lot of activities on making this idea into a reality. By the way, if you have any questions during the talk, please raise your hand. I want this to be a little bit interactive. So for people like me who've been in the field, this is already a pretty compelling application, but you might be wondering at a higher level, like why like simulating like physical systems of interest is actually useful. And it's very simple. So this is not something that face the external like individual consumers directly. But if you think about the technologies that we use every day, like the battery in the car or the solar cells or the fertilizers when you're, if you're a farmer, you do need fertilizers. And in all these things, there's this big effort to, for example, if it's a fertilizer, try to make the fertilizer using the less amount of energy. In fact, this is not a trivial problem, and it's a big problem because it was estimated a few years ago that the amount of energy spent worldwide in generating fertilizer is estimated to be roughly like 1% of the world energy consumption. So it's only 1%, but if you think that this is like the entire energy that all the humans consume, it's a pretty like a sizable amount. And the fact of the matter is, in nature, we know that there are bacteria which can produce fertilizers using significantly less energy than the current procedures that we use. So we know that this is possible in principle. We just don't know how to industrialize it. And moreover, in fact, we actually know the chemicals that we know what this bacteria consists of, basically, but it's just that we don't have a good understanding of how the underlying procedure works. So if you can simulate these physical systems reliably and efficiently, the hope is that you can make big impacts to these large amount of a diverse set of industrially relevant physical and chemical processes. So that is the big goal. And it's important to understand that these are not, we have strong reasons to believe that these are not the kinds of problems that we expect to be able to solve using classical computers. Just like the factoring algorithm, like many people have come up with various new methods to simulate these systems. And in some cases, we did have some success, like density functional theory, for which the Nobel Prize was given. But the fact of the matter is there are some systems for which these kinds of simulation is still very difficult to do. In particular, when the underlying microscopic degrees of freedom, like the electrons, are very strongly interacting with each other. And in some sense, that's the regime that we don't understand very well. So it is expected for those problems, quantum computers are expected to solve them efficiently. Good. So a natural question for anyone who is working on a quantum computer is to do useful quantum computation, like how big of a quantum computer do you need? And once you have a big enough quantum computer, how long of a computation do you need to solve these problems of interest? And this is, you may think this is somewhat unrelated to the field of quantum error correction, but this is actually the big motivating question behind the quantum error correction. So let me start with this one. So I've already told you about these like compelling applications like factoring, material simulation. At this point, so these factoring has been out for like more than 20 years. And in the meantime, people have been optimizing this algorithm like very hard. And it's at this point, we have a number which we think is like pretty close to like the minimal number that we can get. I mean, I'm not saying this is the absolute minimal, but something in the right ballpark. And that number turns out to be between like 1,000 to 10,000 qubits in order to crack the crypto system that we're using, or possibly even the future version. And when it comes down to material simulation, of course, the bigger the system is, you'll need a larger quantum computer, and you're going to need to do more computation. But you can ask, are there any chemical system of interest that we would really like to study right now that seems very difficult? And there are some examples of that. It is related to this like fertilizer example that I told you. In that case, there's a enzyme called MOCO. And in this case, we have like a very specific model of this molecule. So you can write down the quote unquote Hamiltonian that describes the system. And all you have to do is to just solve this Hamiltonian. And unfortunately for a classical computer, this is a rather difficult problem. And if you want to solve that problem using a quantum computer, it is currently estimated that you would need something around the ballpark of like 100 to like 1,000 qubits. So 100 if you want to really minimize the number of qubits, and 1,000 if you want to like sort of increase the speed a little bit. But that's the ballpark numbers. So with these numbers, you might be wondering, like, it's interesting to ask, like, when are we going to get a quantum computer like this? We don't know, but there are some like roadmaps. These kinds of roadmaps like change all the time. So I can't guarantee that all the things here will happen in the future. But this is, for example, one roadmap that was put out by IBM Quantum. So this is kind of small to see, but you know, let me just remind you that this is year 2022. In year 2021, these folks came up with some quantum computer consisting of 127 qubits. So qubit is an elementary unit of quantum computation. You can think of it as a bit. And I told you that to solve these chemical problems, it suffices to have like roughly 100 to 1,000 qubits. And they plan to make this like significantly larger, as you can see in the near future. We'll see what happens, but at least that's the plan. And I don't want to bombard you with like all the roadmaps from all the companies, but more or less, like this is the ballpark number of where the companies are trying to head in the near future. Okay, so that all sounds really great. It looks like we're going to get these large number of qubits fairly soon. So you might be thinking maybe we're not too far away from making this useful applications an actual reality. But there is an issue. So the issue is that the quantum computers that we have today are not perfect. So if you think about it, your laptop or any classical computer that you use right now are pretty much perfect. So if an error occurs, it's most likely because of you. It's not because of the computer. It's for all intents and purposes, error almost never occurs. But in the quantum computers that we have today, every time we apply like even the simplest of computation, there is a non-negligible chance that something bad might happen. That is, there is some non-zero failure probability, which is not completely negligible. So this is a kind of circuit that, this is a kind of diagram that you would see when you look at quantum computing papers. What's happening is that you're starting with some initial states and you're applying what is called as quote unquote gates. This means this is the simplest possible computation that you can apply on like 1 or 2 qubits. So these Sticks diagrams, these correspond to like 1 or 2 qubit gates. And when these simple operations are applied, roughly speaking, depending on the hardware, the chance that a failure occurs ranges between like 1% to, if you're really optimistic, like 0.01%, but that's like really pushing it. So you can see that that's a really big difference between your classical computer. Just to give you an idea, in your classical computer, if you do like integer addition, you can probably do like more than 10 to the 9 integer additions per second, and none of them like fails, basically. So you can quickly see that at the very least, the error rate of the classical computer is much, much smaller than, let's say, 1 over 10 to the 10. So this is a big difference between the classical computing and the quantum computer. And the issue, of course, is that if the error somehow doesn't like mess up your answer, this won't be an issue. But the fact of the matter is, in most of these algorithms, a single error that occurs during the computation can actually yield a wrong answer. Obviously, that's going to be an issue because, well, in the factoring, in that case, the probability that you're going to get the correct factor of a large integer will be very small. So if you want to use these noisy quantum computers to hack something, then it will probably fail. But for material simulation, this is going to be like an even bigger problem because in this case, you often ask questions like, so I have this material and I want to understand what like let's say I want to understand its specific heat, let's say at some temperature. So I want to get some number, and if this outcome gives you like an unreliable number, then I will have no way of verifying if that's actually correct or not, unless I actually go into the lab and measure it. But at that point, like there's really not much point of using a quantum computer anyway. So for these like quote unquote near-term applications of quantum computing, this effective error is like really, really important. So we need to like minimize them somehow. So to be more specific, in order to be like sort of okay with the outcome that we get, the error must happen sufficiently infrequently so that the probability that it occurs during the computation is sufficiently small. In the other extreme, let's say our error rate is like 10 to minus 3, and if our computation consists of like trillions of steps, then like common sense tells us that most likely the outcome that we're going to get will be a garbage. Basically, it will be completely useless. So we want to make sure that we're in the exactly opposite regime of that. Okay, so I already told you that the error rate that people typically have is around 10 to minus 3, maybe 10 to minus 2, 10 to minus 4, something around that ballpark. So you can see that this kind of reasoning tells you that it's not really the number of qubits that matters, what really matters is what's the error rate that you can get in these computers, and what's the how many time steps do you need to actually carry out these useful calculations. So that's a really important thing. Okay, and if that number is significantly larger than 10 to the 3, then we're in trouble. At least the computers that we're going to have in the near future will not be able to do these useful things. So it turns out that, again, if you count the number of gates, which people have done, and at this point, we again have very good reasons to believe that this is likely going to be as low as it gets. These numbers tend to be roughly 10 to the 14, 10 to the 15 gates for factoring. And for material simulation, it's around like 10 to the 10 gates for the problem that I discussed, this fertilizer problem. And the important thing is both are much larger than 10 to the 3. And therefore, if we just naively use the quantum computers that we're going to have in the near future and run these algorithms, like most likely, we won't get anything useful. So how do we deal with error? So in fact, I should emphasize that this fact that there will be a big discrepancy between the error rate that we have in the lab and the error rate that we need to do something useful was not something that we figured out, found out recently. In fact, even right after Peter Shor came up with this factoring algorithm in the mid-1990s, there were very good scientists who raised doubts on the possibility of quantum computing. So this is Bill Unruh. You can find his Wikipedia page. He's famous for it's a different story. But anyway, he's a very good physicist, and he wrote this paper basically arguing that quantum computers are likely not going to work because every time you apply some gate, this qubit will interact with its environment and it will lose its coherence. Coherence means it's some quantum property. So the more you lose coherence, more and more classical this system will get, and eventually your quote-unquote quantum computer will become completely classical, and this quantum power will completely disappear. So the fact that it's hard to achieve good coherence experimentally is one reason to believe that this argument is true. But there are actually also some fundamental reasons to believe that fundamental theoretical reasons to believe why this cannot be true. So the first immediate reaction that you might have against this kind of criticism is that at least classically, we have this very nice thing called error correction. And the idea is very simple. You simply encode information in a redundant way. For example, instead of saying 0, I say 0, 0, 0. And instead of 1, I say 1, 1, 1. So that even if one of the bits are corrupted, with high probability, I can verify where the error has occurred and just correct it. In this case, this would be a simple majority vote. So why not just use this for quantum information? Well, there are some issues. Well, first of all, one thing that you might want to try is something like this. So you start with some, so every computer starts with some initial state. So you start with some initial state, you run, let's say, your Shor's algorithm for the first 10 steps. And then in order to make sure that the error doesn't accumulate so much, you just copy the state of your system, maybe into your quantum hard drive, and make 10 copies of it, okay? And you just go on and check and make 10 of them. So you carry out the computation on these 10 copies. And after 10 additional steps, you check if they're all the same. And some of them might be different from the other. So then you just correct that thing. And then again, keep the 10 copies and just continue. The issue is that there's this theorem called a no cloning theorem. So this idea of copying your quantum state in the middle of the computation actually doesn't work. So if you try to do that, you will fail with some a non-negligible probability, it'll basically never work. So that was the first issue. But then you might think, okay, so maybe we don't copy things in the middle, but we just begin with some we right from the beginning, we begin with 10 copies. Okay, so we start with some simple state, begin with 10 copies, run the algorithm and check if they're the same in the middle. And if they are different, then you just correct them somehow. Well, then there's another issue. The issue is that in quantum mechanics, there's this like basic rule, which we believe to be true, and it's called the collapse of the wave function. So if you look at your quantum state, in quantum mechanics, the word look has a specific meaning. It means that the action of observing your state actually changes the system. And this is fundamental. At least it is believed to be fundamental. We have no reasons to believe that it is wrong. So if you have a single qubit, the state of the system can be described by some complex numbers like alpha and beta, which is important. And it is important to keep this information to keep this power of this quantum computer. But in the process of like observing this qubit, you end up collapsing this into 0 or 1, at which point this information about alpha and beta is completely gone. Another issue is that in quantum computing, there can be this thing called phase error. So in the classical case, you simply have two states, a 0 or 1, and 0 is sometimes flipped to 1 and vice versa. And quantum computing, sometimes this alpha and beta, being a complex numbers, may undergo a different evolution, and alpha may remain unchanged, but beta might change. And this will also cause an error. So it was pretty surprising when Peter Shor in 1995, like right after coming up with the factoring algorithm, showed that quantum error correction is in fact actually possible. So this really was the main reason why this quantum computing field could jumpstart, because it showed that building a quantum computer, it may be a difficult engineering task, but fundamentally, there is nothing that is preventing us from doing so. So let me just briefly tell you about the ideas behind the error correction. So apologies for the handwriting, but I think it would be better this way. So basically, the idea of like quantum error correction is that you want to correct two kinds of errors. So one kind of error is something that you're familiar with. It's called as a bit flip error. This just means that you're changing, it's an error that changes 0 into 1 and vice versa. It's a kind of error that you encounter in classical error correction as well. So here's an example. So let's say I have 3 qubits and they're in the state of alpha 0, 0, 0 plus beta 1, 1, 1. The bit flip error, what it does is that it can flip one of the qubits. So for concreteness, I'll say that I flipped the qubit number 2, the guy in the middle here. So that means that 0 is flipped to 1 and 1 is flipped to 0. So you see that 0 indeed gets flipped to 1 and 1 gets flipped to 0. And one thing that is allowed in quantum mechanics is that you can check two things, or these two bit values are equal to each other or not, without actually measuring the individual bits. So you might think this is a very strange thing, but this is allowed in principle, and people have done the experiments for it. I'm going to talk about that later. So what you can do is that even without, if you measure the individual bits, you end up collapsing the wave function. But it is possible to check whether this qubit number 1 and qubit number 2 are equal or different from each other without collapsing the wave function. So you can do that. You can check whether qubit number 1 and 2 are same or not, qubit number 2 or 3 are same or not. And that's some information that you can like write down on your like notebook or something. So 1 and 2 are different and 2 and 3 are different in this case. So knowing that information, what you can do is that you can simply apply the right correction, which in this case is just flipping the second one. So this is possible. What we achieved is that we were able to correct a single error using essentially a classical error correcting code, but without collapsing the wave function. And what's interesting is the exact same thing works also for this phase flip error. So the phase flip error is basically changing the amplitude alpha and beta by an overall factor of -1. So I won't go through it one more time because it's pretty much the same story. But here, what you're doing is that you're using a different encoding. So instead of like 0 and 1 state, in quantum mechanics, you can create these like so-called superposition states. And these other states can be used to protect against phase flip errors. So what these examples show is that if you only know, if you know that there's only going to be bit flip error, then you can correct it. And if you know that there's only going to be phase-width error, you can also correct it, even in quantum mechanics. And the crucial observation by Peter Shor was that you can somehow like concatenate these things together so that you can correct both the bit flip and the phase-width error at the same time. At least that was the first. That's how the first quantum error correcting code was discovered. Good. So you might think that at this point, having the fact at this point the fact that you can build a quantum computer is a rather straightforward thing, but there is like one caveat, namely, let's consider the following scenario. We're back to this bit flip case. So let's say the qubit number 2 was bit flip. So again, this is pretty much the exact same slide as before. So you see alpha 000, beta 111, and I get 010, beta 101. And then what I want to do is that I want to check again if these the qubit 1 and 2 are different or same, and qubit 2 and 3 are different or same. The catch is when you check if they're the same or not, that process might go through an error as well. And when that happens, well, this is a simple example so we can see exactly what's going on. So let's say I made a mistake here. So we know that 1 and 2 are actually different, but let's say I somehow, my experimental gadget produced an error and it told me that they're actually the same. Well, in that case, what's it? So 1 and 2 are the same and 2 and 3 are different. So if that's the input that we got, we're naturally led to believe that it must be qubit number 3 that should be flipped, not qubit number 2. So after you do that, you get this state 011 plus 100, which is not what you want. So as you can see, simply coming up with a quantum error correcting code is not the end of the story. You still have to make sure that even if everything fails, you can still do quantum computation. And that took another year to figure out. And I should note that this study of can you do computation when everything fails is actually can be found in its classical roots. So back in 1945, computers used to look like this. As you can imagine, they were not exactly error-free. So there were motivations to think about this problem. So like if every individual components of your computation fails with some probability, then what do you do? And von Neumann established this theory, which showed that theory of fault tolerance, which showed that even in that case, you can perform classical computation for an arbitrarily long time. And you have to pay a little bit of overhead to do the error correction, but that overhead is like not too much, maybe like logarithmic in the size of the computation. So in the grand scheme of things, like it's not like a huge cost. And fortunately, many, I wouldn't say the techniques that was used back then directly applies, but certainly many of the spirit of these techniques still apply to quantum computing. And these people, Aharonov, sorry for the typo, and Ben Orr in 1996 showed that provided that every failure rate is sufficiently small, as long as you scale up the system, you can make the overall error rate arbitrarily small. So that is to say, even if like every single component of your quantum computer fails with some probability, as long as it's smaller than some number, we call it as a threshold, then we're good to go. Then we can still do effectively like error-free quantum computation. So it's really this result that told us that quantum computation is possible even in a realistic, quote unquote, in realistic condition. By realistic, I mean in which case, the case in which all the components may fail. So that led to the early era of quantum error correction from 2000 to 2020. And in this era, the main overarching theme is a number called threshold. It's an important quantity / concept. So I told you in the previous slide that Aharonov and Ben Orr showed that in 1996 that if the error rate is below some constant, then you can do an essentially arbitrarily long quantum computation with like practically zero error. And that number is called as a threshold. It's some constant such that if you're below that constant, it can do an arbitrarily long quantum computation, almost perfectly error-free. But if you're above that constant, then the error will sort of like overwhelm your system, and you won't be able to correct the error anymore. And this is a kind of plot that you will often see in this kind of paper. So in the x-axis, what you have is the physical error rate. So the probability that the individual component might fail. So as you go to the right, the error rate increases. So that means that the quality of your component is worse. In the y-axis, we have what is known as the logical error rate. It means the error rate after you apply the error correction. So what we want is obviously this number to be like lower, because that means the failure rate is lower. And you can see there's a pretty dramatic difference along this to the left and to the right of this like dotted line. And this line is where the threshold lies. So if you're like below this threshold, you see these many plots. And what do these plots mean? They say D, which is this can be thought as your system size. So as your system size increases from 3579, all the way to 555, you can see that the logical error decays like very, very rapidly, as long as you're below the threshold. In qubits or in gates? These are qubits. Yeah. But on the other hand, if you're above the threshold, like just making your system simply doesn't help. And actually, it just makes things worse, right? So this, you may not be able to see it, but at least here's the D equals 3 line, and here's the D equals 55 line. So we have this like a single point threshold, so that if you're above the threshold, you have too many errors and you can't correct it. If you're below the threshold, the errors are low enough that you can correct it, and you can just perform like pretty much error-free computation. So obviously, based on, so this is a typical plot that you'll see in quantum error correction literature, and obviously what you want is very simple. So we want the actual error rates in the experiments to be lower than the threshold that we can achieve. So this threshold value, it depends on a lot of details, but in particular, it depends on the error correction scheme. But error correction scheme is something that a theorist can invent. But at the end of the day, we got to have an experimental device which has which can go below the threshold that the theorist proposes. So that has been like one of the big goals in the field of quantum error correction. And indeed, there has been many progress. So so this is an exemplary plot of like what you'll see when you look at the historical performance of like various quantum computing technologies. This is the case of the superconducting qubit, and x-axis is obviously year, and in the y-axis, what we have is so-called the coherence time of the qubit. Roughly speaking, it's not exactly the same thing, but the larger the coherence time, you get a lower error rate, because the qubit is effectively more shielded away from your environment. And as you can see, you may not think that this is a very like rapid growth, but notice that this is a log plot. So this is actually sort of an exponential growth in time, the coherence-wise. And so there has been progress on the experimental front like this. And also on the theory land, by we, I mean like many of my colleagues, managed to increase the threshold from this like very daunting number of 10 to minus 6 to a number that seems like more manageable, which is around like 10 to minus 2. And finally, in year 2014, this is the year that I remember very vividly, because I saw this paper for the first time. And the paper was from the UCSP group, which later then became part of Google. And they reported a superconducting quantum circuit consisting of, I believe, like 9 qubits. And the important thing is all the qubits were below this threshold value. So this really was like a strong evidence that we could actually build devices that are below the threshold. And at least from a theorist perspective, like myself, then our natural thought was that now all we need to do is to like scale up this system while maintaining the same level of coherence, and then we'll be able to build a quantum computer. And I think that kind of optimism really boosted the confidence in the field like quite a lot. And in fact, the blueprint for building a quantum computer that has these high thresholds of around 1% are not totally crazy. So if you look at how this architecture looks like, it looks like the following. So basically, you see these like white and dark dots. These are where the qubits lie. And all you need to do is to be able to apply some entangling gates between the neighboring qubits. For example, this qubit and that qubit. So if you can do that while maintaining this error rate of around like 1% or less, then by simply scaling up that system, you can build this fault-tolerant quantum computer, which can make the logical error rate arbitrarily small. So then the long-term goal became to make this an actual reality. Good. So so that was more of a background. So I'm going to tell you more about the recent developments. Some of them will be related to my own work, but some will be related to some of the works that the future speakers will be talking about. 10 minutes. Okay. So first thing that I should say is that there has been a lot of progress experimentally. So I told you that people were able to build these devices already in 2014 below the threshold. But it's one thing to build those devices. It's another thing to actually demonstrate that the error can be corrected so that after the error correction, the error is like lower than what you have at the physical level. And I want you to focus on the date, 2022, 2021, and 2022. These are like results from like various experimental groups. And people have been starting to indeed report that, like actual demonstration of quantum error correction, such that after the error correction, you get a lower logical error rate than before. So it's no longer not just like a theorist's dream, it's something that you can actually demonstrate in the real lab. So at least in this field, the questions that theorists ask tend to be somewhat a few years ahead of what the experiments can achieve. Like this is not always the case, but this is the case in this field. So what people have been thinking about was the following. So it's clear that at this point, quantum error correction just works. I think there's no doubt about that. Then like if we were to actually make a scalable and like efficient system out of this, then what should we do? This is a question that people in so-called like quantum computing architecture asked about a lot of the times. So I wanted to give you like sort of a broad overview of this field. And I think it's really a fascinating field because it really covers really low level physics and optimization to like a really high level like mathematical thinkings. So let me first, I think it doesn't take a genius to see that there is an intense need to look at the low level and see what's actually going on. But let me give you like an example. This is a classical example. So this is a CD, in case you don't know what that is. It's people used to listen to music in this thing. And I can't believe I have to explain this, but when you actually listen to this thing spins around. And the thing is, because of that, the CDs might get broken, and when it does undergo an error, the error doesn't really follow the pattern that you would think you would in the theory land. So in the theory land, you would believe that there is a identically independent distributed errors on all the bits or something. But if you actually look at the error pattern that appears in these devices, it sort of looks like this. So like the idea is that if you, for example, push the CD, then you can sort of imagine there's some like little glitch and the CD is spinning. So you can sort of get this like burst of error. And what's interesting is that even like classically, people really looked into these details and used an error correcting code that is like more robust against these particular kinds of errors. And indeed, this kind of thing is not just restricted to classical case. Also in the quantum case, there are a lot of details that has to go on. And indeed, like, so I told you that in Shor's error correcting code, you can check whether there's an error occurred or not. But the process of how to checking that error, there's a lot of details on how you actually do that. And depending on how you do it, you really get a drastically different result on the threshold. So that's something that people have been working on. And this kind of like details does seem to matter quite a lot when you go into explicit like hardware implementations of these quantum error correcting codes. So here's one example. So here's one of the works that I did, and it's one way to build a quantum computer. And it's based on a very simple setup. What you have is you have a single quantum emitter, and what it does is that it's emitting photons, and the photons go through these delay lines and comes back to the emitter and interacts with the emitter, goes through another delay line, interacts twice, and goes out. And then the quantum computation is performed by detecting these photons in particular bases. Now, if you look at the circuit, it looks like this. So this, what you have is this single quantum emitter that is keep interacting with all the individual photons. And this makes sense because the photons were emitted from the emitter, and then every single photon actually interacts with the emitter in the future again. So you can sort of imagine like a single error that are occurring in this like quantum emitter may propagate to all the errors in the of the photons. Sort of similar to this like a CD example. So like you like push once and it just makes a scratch on an entire line in entire circle. But what's remarkable is that despite the obviously the main motivation for making up with this setup is that this is like significantly simpler than having like a large number of qubits and controlling them individually. And by looking at these microscopic details, you can actually see that there can be still a threshold. So this is the kind of plot that you would see in these kind of schemes. And that threshold value is a little bit lower than like 1%, but not too far. Like it's around the order of like 0.4%. So like looking at these details do seem to give us a lot of leverage in building these fault-tolerant quantum computers with relatively less resource. And once you build these fault-tolerant devices, well, the experiments that people have been doing so far has been primarily focusing on showing a preservation of quantum information. But if you think about it, what we really want to do with quantum computers is not just like storing information. We want to actually manipulate them so that we can do non-trivial computation. And another thing, the key subject of the field of quantum computing architecture is how to apply gates in these information in a protected way. And that turns out to be an interesting subject because naively, if you know what a qubit is, you tend to think a qubit as a very continuous object. So the state of the qubit can be morally thought as some vector that is pointing on a sphere. This is the block sphere. And the gates are some transformations that rotates these vectors. And obviously, this is just a sphere. So the set of gates that we can apply on the qubit seems to be continuous. And that is indeed true. So if you, let's say in your lab, turn on your magnetic field and measure the polarization, then like you often see a plot like this. And so the point is, like, depending on like how long of a time you turn on the magnetic field, you get this like oscillating plot, which seems fairly continuous. What's maybe not so obvious, but what is true is that the fault-tolerant gates, the gates that we know how to protect, do not form this like continuous set actually. So what is not obvious is that even so, you can still perform universal quantum computation, but how you actually do this in general is not a trivial problem. So some of the things that I've been working on is precisely trying to understand how this can be done. When it comes down to this architecture that I showed you on how most companies are trying to build this planar architecture, at this point, we have like a good enough understanding that we have a variety of options on how to implement these gates, the universal gate set. But more recently, there has been a new class of codes. These are called as LDPC codes And these are like somewhat more exotic in a sense that you cannot arrange them in a planar fashion. You'll need to be able to apply gates between qubits that are very far away from each other. But the upshot is that these codes are in a way more efficient than these planar codes. So with the same number of qubits, while maintaining a same level of protection, you can encode like a more information into the same number of qubits. So in the future, so this probably won't be like a very near-term thing, but in the future, you might imagine building a quantum computer by leveraging these codes. But what has not been obvious is to how to apply actual gates on these systems. So these were good for protecting information, but applying gates has been somewhat difficult. But fortunately, I guess I won't have much time to discuss this. But now we have a pretty general method to apply gates, and again, this will be a universal gate set. So yeah, so what am I trying to say? So in this talk, what I wanted to show you was the basic history behind quantum error correction and what I do in our research group. And I think the key takeaways are the following. The first is that at this point, the fact that you can do error correction and suppress error is settled. This is settled in theory a long time ago, and this is like surely settled by experiment at this point. And now the question is like how to make them like more efficient, how to make the quantum computer bigger and faster so that you can do actually something useful. And in that respect, quantum error correction will play a crucial role, and in particular in this like nascent field of quantum computing architecture. Okay, so thanks for listening. I'll be happy to answer questions.
Thank you for a fascinating talk. Are there any questions about the students to ask before calling on that? Yeah, please. I was just wondering, you talked about the reports for LSC, so like there's like another subfield like quantum AI. So does that do that?
Right. So quantum AI. So I should note that I'm not an expert in quantum AI. So I think quantum AI primarily pertains to the application of quantum computing, whereas this is about like building a quantum computer. That said, there has been some interesting work on how to make these error correction procedures more efficient using AI, like neural networks.
So for the UPC code, it looks like in the architecture drawing there are multiple layers. Is that something that like IBM is trying to work with, or they get better at swapping different?
Oh, yeah. So I'm not sure. So at least publicly, I'm not aware of any such plan. Basically, I'm not aware of any companies which are trying to incorporate this very seriously yet. This is mostly because there are some like practical challenges. So for the surface code, you can sort of make things like gradually better. So you start with the 10 by 10 surface code, 11 by 11, and as you increase this number, you get like increase the number of qubits very modestly, while like just smoothly decreasing the error. But the LDPC codes, so far, the ones that we can construct are somewhat sparse. So like maybe an analogy would be this. So in LDPC code is really some code family. So in code 1, you have like 10 qubits, and in code 2, you're going to need like 2,000 qubits. And the next one, you need like 300,000. So we don't have this like a very smooth thing. So when we have like a small number of qubits, it's kind of hard to fit your future architecture into these things that are not somewhat sparsely distributed in this theory space.
Okay, I was wondering, like, how do you know when an error happens?
Right. Yeah. So it's a good question. So we actually so what we do is that so in this bit flip example, we checked whether 2 qubits, their bit values are equal or not. So it's basically an analog of that. So it's for example, if it's something like this. So maybe you have like 4 qubits, and you want to check if an error has occurred in any of them. So we're not too interested in whether an error occurred at a specific location, but we just want to know whether whether an error occurred somewhere. And to do that, it suffices to basically check the parities of the bits. And that's something that you can easily do. And then it's the job of the decoder, which is just a classical algorithm, to find the a best recovery pattern based on what you observe. Yeah. Mm-hmm. Right. So yeah. So it's a good question. So we have very good reasons to believe that this is an exponential decay in D. So so let's see. Yeah, I see what you mean. Oh, okay. So I should note that it's an exponential decay in D. It might be power law for P. So so let's see. Yeah. So the logical error decays exponentially in the size of the system, and it's probably power law in terms of the physical error rates. It's something like physical error rate divided by some constant raised to the power, which is proportional to the system size. Yeah. And that we have very good reasons to believe that's true.
Since we're able to compare the two qubits are the same, are we able to run two identical copies on it and then essentially run them together in the same circuit to check if those two bits are the same around collapsing?
Right. Yeah, it's a good question. So we generally cannot. So well okay. So actually, so there actually is a way to check if these two identical computations are really producing the same state. But the trouble is that when, let's say we checked it and we verified that they're different, then it's unclear how to correct them, even if you have 10 copies of this. So I guess the point of this error correction protocol is that when you know that they are different, based on the pattern that we get, we actually have a decoding algorithm that tells us how to correct it. So that's actually something that I push under the rug, but that's an important part. And indeed, generally, it's not easy to come up with that, how to decode. That's a separate hard problem, but we know how to do it.
So it goes back to kind of more like the beginning, but when you have a bit flipper, that's discrete to values 0 and 1. When you have a phase flipper, it's approximated as if it's a discrete situation, but you can flip from minus to plus or minus to I or minus I.
Yeah. Right. Yeah.
Is that the practicality or of simplified, or is there more fundamental reason why we can do that?
Yeah, it's a good question. So there's a reason why we can do this without losing any generality. So let's say I have this more continuous error. So I apply some continuous phase on 1 and don't apply phase on the 0. Then you can do what you can do is that you can still check whether this process of checking whether two bits are the same or not. You can still do that calculation. And then what you see is that you actually collapse the wave function in this case, but you collapse in such a way that this continuous error collapses into a discrete error. So this process of checking the error collapses the wave function, but in a good way. So that's the answer. Yeah.
Last question. If not, let's thank Professor Chu again. See you next week, the virtual session.
Right.
So we have